Today we're looking at inverse variation. We're actually going to go back and revisit direct variation, which you learned in Algebra 1. So we'll start with that and then move to inverse variation and then some others that we call combined variations, okay? Specifically joint ones as well. So if a product is constant, where the constant is positive. So let's say we have a product of x times y equaling 5. Okay? A decrease in the value of one factor must accompany an increase in the value of the other. In other words, if I make x get smaller, I'm going to have to make y get bigger to compensate if I want to keep a constant 5. Does that make sense? Okay. So when we look at variation, as I said before, we have direct variation, we have inverse variation. Direct variation is basically a line through the origin, y equals mx. We just don't have the b part in there, all right? But instead of an m, we use a k. It represents the constant of variation. Okay, so y equals kx is a basic direct variation equation. If we were to solve that for k instead, we would have to divide our x to the other side. So we would get this version of it, y divided by x equals k. In a direct variation problem, that k is a constant. Okay? For inverse or indirect variation, we start out with y equals k divided by x. If we were to solve that for k, we multiply our x to the other side, and we get this. So that's what I was referring to up here. If we have a product that stays a constant, when we increase one value, we have to decrease the other. Okay? Now, where students typically get confused by these is they try to memorize which one's multiplying, which one's dividing. But it depends on which form you're looking at. When you are solved for y, we have our constant times x equaling y. When we solve it for k, it now becomes division, y divided by x. So don't try to memorize it that this is the one where you're multiplying or this is the one where you're dividing. Pick either version, either solved for y or solved for k, and memorize that version of it. You can always rewrite it the other way if you need to. Okay, so y equals kx is how we're going to start our direct variation, and y equals k divided by x is how we're going to start out with our inverse variation. All right, so our first question, it says identify if it's direct and inverse. It could be neither, so keep that in mind. If it is direct or inverse, they want us to come up with a model for that. Okay, so the first thing I would do is I would look at my numbers and compare y equals k times x, which is our direct. Our inverse one was y equals k divided by x. Okay, so we're going to look at our table and decide which of those seems to fit. If I solve this for k, we said it was y divided by x. In other words, if I take all of my y coordinates, divide them by their x coordinates, I should end up with a constant. All right, so we check it. Is 15 divided by 2 get me the same thing as 7.5 divided by 4, or, 3 divided by 10? Are those getting us the same thing each time? If we take our y value divided by our x value? No, we're not getting a constant. All right, so since those are not equal, it's not direct. Then we check to see, is it inverse variation? Y equals k times, y equals k divided by x, so x times y would now have to give us a constant. Checking that. If we take 2 times 5, if we take 4 times 7.5, if we take 10 times 3, 15 times 2, do we get the same answer every time? Whoops, 15, sorry. 2 times 15 is 30. 4 times 7.5 is 30. 3 times 10 is 30. 15 times 2 is 30. What we have found is our constant of variation. That 30 is our k value. So the model that we would give for this one, we'd say it's an inverse variation, And the formula is y equals 30 divided by x. Okay. Let's look at the second one here. Again, we are checking to see is it direct or inverse or neither. Direct is like that mx plus b kind of equation, y equals kx. Inverse is k divided by x. All right, so again, solving for y. If we take our y values and divide them by x, do we get the same thing? 10 divided by 2 is 5. 8 divided by 4, so we're not getting a constant, right? So it's not direct. If we multiply them, x times y, do we get a constant? So 2 times 10 is 20, 4 times 8 is not 20, right? So if it's not direct and it's not inverse, we say neither. Okay? I'm going to pause the recording. I want you guys to try the next example. All right, so we've got our basic direct and inverse variation equations. Again, solving for k to check to see if we have that constant. What is 8 divided by 2/10? Okay. What is 20 divided by 1/2? What is 40 divided by 1? And what is 60 divided by 1.5? All right, so is it direct? Yes. Our constant is 40. So the model that you would use, y equals 40 times x. We're just taking that k value and plugging it in. Okay? Questions about identifying the type of variation? All right. This one says, suppose x and y vary inversely and x equals 4 when y equals 12. I've kind of split this up into several parts of the question because students often try to skip over some steps. It says, suppose they vary inversely. Right away, you should be writing down your inverse variation formula. Okay, so we're going to start out. Y equals k divided by x. Then it tells us that when x is 4, y has to be 12. So they're giving us an ordered pair that has to work in that equation. So we're going to dump those two values in for our x and y and use them to figure out what our k has to be. So when x is 4, we are supposed to get 12 for an answer. Multiplying the 4 over, we end up with 48 for our constant. Now we can do what they said. We want a model for this. So y equals 48 divided by x. Okay, that's the first part. Then it says, what does the graph of this function look like? For this first one, we are going to plot a whole bunch of points because I really want you to see what the shape is. After that, we can cut back a little bit and just have enough that we can sketch it in. Okay? So I've chosen numbers for x that divide into 48 nicely. All right, so we don't have to worry about decimals. So our equation was y equals 48 divided by x. So what's 48 divided by negative 12? Okay, divided by negative 8, divided by negative 6, and dividing by negative 4. Okay, let's plot those first. Notice that we are going by 2's here. Okay, so at negative 12 for x, we are at negative 4. Sorry, I said we're going by 2's and then I didn't go by 2's. Negative 12, negative 4. All right, negative 8, negative 6, negative 6, negative 8, and negative 4, negative 12. Okay, so that is half of our graph. We have a branch here. Now let's look at what happens when we put positive values in. If we put a positive 4 in, we get positive 12. Negative 6 gives us a positive 8. Positive 8 gives us a 6. And 12 gets us a 4. Okay, so now we plot those. All right, 4, 12, 6, 8, 8, 6, and 12, 4. That is a shape that you're going to see a lot of in this chapter. All right, it's a basic rational function. You guys have been graphing parabolas, x squared graphs. You guys have been graphing absolute value graphs this year, all kinds of things. This is a rational equation. All right, y equals k over x. The third part says, what is y when x is 10? Well, we have our equation. All we have to do is plug a 10 in there. Okay, so y equals 48 divided by 10, so 4.8. Okay? All right, our second example of that. Suppose x and y vary inversely. So again, they are telling us the basic framework to use. Inverse variation, y equals k divided by x. Then they are telling us when x is 8, y has to be negative 7. Okay, so we put a negative 7 in for y, we put an 8 in for x. What do we get for our k value? All right, so the model that we would list for this one, y equals negative 56 divided by x. All right, I'm going to pause the recording. I want you guys to fill in your t-chart and plot your points. All right, so using our y equals negative 56 divided by x, if we dump a negative 8 in there, what do we get? 7. Put a negative 7 in for x, we get 8. Negative 4, 14, positive 4. Negative 14, positive 7, and positive 8. All right, so plotting those. Negative 8, positive 7, negative 7, positive 8. Negative 4 puts us up at 14, right? It's a little off our graph. What would happen if we put a negative 14 in for x? Then we'd get a 4, yes? So we are still getting that curve. Okay? And then you should have a similar branch over here. All right, so let's see, 4. We were at negative 14. 7, negative 8. Now I want you to compare the two graphs that we've done. In this graph, we had a negative k value, and we were in quadrants 2 and 4. On the other one, we had a positive k value, and we were in quadrants 1 and 3. Okay? So you should know just by looking at the equation which quadrants your graph should land in. It's always going to be in opposite quadrants, so 1 and 3 or 2 and 4. Okay? All right, the last part of that question was, what is y when x is 2? So if we put a 2 in here, we get what? Okay. Questions on that process? All right, we're going to look at some data and check to see how we can use our inverse variation to model that. It says your math class has decided to pick up litter each weekend in a local park. Each week there's approximately the same amount of litter. The table shows the number of students who worked each of the first 4 weeks of the project and the time needed for the pickup. So what happens as the number of students increases? What happens to the time that it's going to take us to do the job? It goes down, right? The more people working, the faster it gets done. Okay, so as one quantity increases, the other decreases. What type of variation are we guessing? Inverse. Okay, so let's check. If it fits y equals k divided by x, then x times y has to stay constant. Okay? Now, we are working with data. It may not come out exactly the same, but it should be really close. Okay? So, multiplying. Take 85 times 3. Take 5 times 51. Take 12 times 21. Take 17 times 15. What do we get for answers there? 255 for the first one? And the second one? Okay. Okay, thank you. All right, so we're getting 255 3 out of the 4. All right, so we're going to let that be our k value. All right. Now, what model can we write for this? Normally we have y equals k over x. Notice that they did give us different variables to use. They said time is t. That would be like our y before, and n will be number of students instead of our x. Okay? So instead of y equals k over x, we would say t equals k divided by n. And we just said our k value was 255. All right, so that's the model for this. Now it says, how many students should there be to complete the project in at most 30 minutes each week? What does at most mean? No higher than that, right? We don't want to go over 30 minutes. So we are looking for our time to have a limit of 30. So 255 divided by n, we want to keep 30 as the max. So it can be less than or equal to 30, but we don't want to go higher. How would we solve that? What can we do? Multiply this over? Okay, so 255 has to be less than or equal to 30n. Then can we divide the 30 to the other side? So 255 divided by 30 has to be less than or equal to n. What do we get? Right, 8.5, we can't have half a student, so we would say n has to be less than or equal to Okay, I'm hearing 8, I'm hearing 9. I'm going to pause the recording. I want you guys to talk at your table. Which one's going to work? All right, so if we read this, 8.5 has to be less than or equal to n. If I read it from n, I'm saying n, the number of students, has to be greater than or equal to 8.5, right? N has to be greater than or equal to 8.5. I can't go down to 8. I have to round this up to 9. Because if I have 9 kids, the job's going to get done faster, right? 8 kids isn't enough. I needed 8.5 kids to get it done in 30 minutes. Since I can't have a half, I have to go up to 9 kids. Does that make sense? Then they'll finish it a little less than 30 minutes, which is okay. We just don't want to go above it. Does that make sense? Yes. Okay. After a major storm, your math class volunteers to remove debris from the yards. The table shows the time t in minutes that it takes a group of n students to remove the debris from an average-sized yard. What function models the time needed to clear the debris relative to the number of students who do the work? And then how many students should there be to clear the debris from an average-sized yard in at most 25 minutes? All right, I'm going to give you guys a minute. I want you to figure out what your constant of variation is. What is your value for k? All right, so we need x times y to be a constant. Yes? So 1 times 225 is 225. 3 times 75 is 225. 4 times 45 is, sorry, 5 times 45, thank you. 5 times 45, 225. And 14 times 16, 224. Close enough? We're going to go with 225? Okay. So our model is t equals 225 divided by n. This time we want the time to be what? At most 25 minutes. So now we have to be 25 or less. Okay. So 225 divided by n has to be less than or equal to 25. So can we multiply the n up and divide the 25 down at the same time? All right. So 225 divided by 25 is less than or equal to n. What do we end up with? 9. So our n value has to be greater than or equal to 9. We would need at least 9 kids. Could we have more? Yes. If we have more than 9 kids, we'll just get it done faster. Okay? All right, the last piece that we're going to look at. We've been talking about direct and inverse variation. We're going to look at a couple other types. These are called combined variations. It just means that we're going to throw a few extra variables in there. Sometimes we might mix inverse with direct variation, combine them. Bless you. It says when one quantity varies directly with 2 or more quantities, we have what's called joint variation. So the two terms, combined just means we have multiple types of variables involved, different types of variation involved. Okay? Joint variation means we are looking at direct, but with many variables. Okay? All right, so our example, it says the volume of a cone varies jointly with the area of the base and the height of the cone. Do you remember that formula from geometry? Volume of a cone is 1/3 the base area times the height. Okay, so this 1/3 is our constant of variation. That's our k value. We're multiplying by b and h, similar to y equals k times x, direct variation. So we have direct variation because our constant is getting multiplied to our variable, but we have several variables. So that makes it a joint variation. Okay. I've put a few examples on here. You want to be able to go back and forth. Looking at an equation, could you describe the kind of variation to me? Versus looking at the description and writing the equation. Okay? So this first one, it says z varies jointly with x and y. That means it's a direct relationship, but with more than one variable. All right? So we have z equals k times x times y. There will always be a k in your variation equations to represent your constant. Okay? The variable that it says varies somehow, so z varies, means I'm going to put z equals. All right? Z equals some k value and then I have to figure out what I do with my other pieces. In this case, it was joint variation, meaning they're both directly related. Okay. The second example, z varies jointly with x and y, so just the same thing we had earlier, and inversely with w. So think about an inverse variation. Our x was in the denominator. All right. So now we have the z equals kxy that we had from our first example here, but we've added that dividing by w. We've included an inverse variation with w. Third one, z varies directly with x, so z equals kx, and inversely with the product wy. So when it tells you something is a direct one, you're going to put it in the numerator. When they tell you it's an inverse one, you're going to put it in the denominator. Okay? So if I give you this equation, how would you describe that to me? We'd start out with y varies directly with x and w. Now we could also say jointly, because a direct relationship with two variables, two or more, would be called joint. So y varies jointly with x and w, and inversely with, and you might see m squared or the square of m, something like that. Does that make sense? Okay. So we're going to look at one that has multiple variables here. It says the number of bags of grass seed N needed to reseed a yard varies directly with the area A to be seeded and inversely with the weight W of a bag of seed. Now before we get into all the specifics, the numbers they're giving us that will help us figure out our K value, let's just set up our equation. The number of bags N varies, so we're going to start out N equals, right, and some constant of variation. N equals some constant. It varies directly with the area. So am I going to put area in the numerator or denominator? Numerator. And inversely with the weight. Where does the W go? In the denominator. Okay, so we've set up our basic formula. Now it says, if it takes 2 3-pound bags, so the 2 is going to be for what variable? N. N stood for the number of bags. Okay, so this is N. The 3-pound bag is the weight of the bag. So 3 is W. And then it says we want an area of 3,600 square feet. So we're given an N, an A, and a W. We can use that to come up with our K value. So N is 2. Our area is 3,600. And our weight was 3. So to solve this, I have a couple options. Can I just do 3,600 divided by 3 and simplify that piece? I could do that. The other option would be to multiply the 3 to the other side. I'm going to end up with the same answer either way. When you look at this, what would you pick? Would you multiply the 3 over? Okay, we can do that. 3 times 2 is 6, so 6 equals K times 3,600. Then what would we do? Divide out the 3,600. So what is 6 divided by 3,600? 1 out of 600, 1/600th. Okay, so our K value, we need to plug in there. So N equals 1 out of 600. And then we said our A has to be in the numerator and our W has to be in the denominator. Okay? So we've got our model for this specific data. Now it says, if this is the case, how many of those 3-pound bags will we need if we need to seed 9,000 square feet? So how many bags do we need if our area is 9,000 and our bags weigh 3 pounds? So 9,000 divided by 1,800 is 5. So we need 5 bags. Okay? So keep in mind, students want to try to throw all the numbers in at once. But did you see that we kind of split that? Use the first part to figure out your K value, then apply it to a new situation. All right, we've got one left. I think we have one left. All right, it says gravitational potential energy, PE, is a measure of energy. PE varies directly with an object's mass and its height. PE varies directly with an object's mass, m, and its height, h, in meters above the ground. Physicists use a g to represent the constant of variation due to gravity. All right, so instead of a k, we're going to use a g. So, PE, potential energy, varies. We're going to have a constant of variation. Again, they are using a g for gravity. It varies directly with its mass and its height. So they also could have said jointly, right, because it's a direct variation with more than one variable. So with mass and height. It says the skateboarder in the photo has a mass of 58 kilograms. So we're going to put a 58 in for mass. And it has a potential energy of 2,273 and 6/10. And in the picture, what is the height? 4? All right. How would we solve for G? Okay, so let's figure out 58 times 4. What do we get? Okay, so 232G equals 2,273.6. Now divide out your 232. What do we get for G? 9.8? Does that look familiar from science class? Okay, the effect of gravity. So let's write our equation now. We found out our G value. So potential energy equals 9.8 mH. 9.8 times mass times height. Now it says, what is the gravitational potential energy of a 65 kilogram skateboarder on the same half pipe? So we're going to still put in a height of 4 meters. Its mass is now 65. What do we end up with for their potential energy? 2,548 joules. Okay? Questions about that? All right, so your homework assignment is listed there.